Hello everyone, welcome back to my channel, and in this video we are going to talk about a very interesting function. Okay, we all know about continuous functions, right? And there are many functions which are continuous everywhere in R, right? But similarly, is there any function which is continuous nowhere in R? The Dirichlet function, which looks like this, right? The value of the function is 1 when x is rational, and the value of the function is 0 when x is irrational, right? And obviously the function is defined on set of real numbers. Okay, now this function is discontinuous everywhere in R, right? So this function is discontinuous everywhere in R. So this is the main property of this function, right? A function which is discontinuous everywhere in R. Okay, so now this function gives us the idea about some special kinds of functions which also behaves like this function, right? So now the idea behind this function is to take two different values for rationals and irrationals individually, right? So now let's take a function. Okay, so now let's take this function. So the value of the function will be -2 for rationals, and let's say 29 for irrationals, right? Okay, so now this function behaves the same as the Dirichlet function, as I've told you that we have taken two different values. Okay, so one is -2 and one is 29 for rationals and irrationals individually, right? Like for rationals it gives us -2, and for irrationals it gives us 29. Okay, but now the question is, why are these kind of functions discontinuous everywhere in R, right? So let me draw the graph of Dirichlet function. So this is the fx. Okay, this is the x. Okay, this is 1 and this is 0, right? So now for Dirichlet function, our rational values will give 1, so there will be some dots at 1. Now look carefully, it will not be a straight line, as we know that between two rational numbers there are also irrational numbers, so we cannot, and for irrational numbers the value of the functions give us a different value which is 0, so we cannot straight up draw a straight line, right? So and for irrationals we will get some dots at 0 like this. Okay, to call a function continuous, the function must satisfy this condition. So the limiting value at the point A must be equal to the functional value of A, right? So now in this case we can get or evaluate the value of fa. If a is a rational number, then it will be 1, and if a is an irrational number, it will give us 0, right? But for the limiting value, no matter how much we zoom in, so let's say this is the point A, okay, on the real line. So now no matter how much we zoom in, okay, we will always find a neighborhood where the values, so let's say we have taken a neighborhood of A, so there will be always rationals and irrational numbers. So for this, the value will jump between 0 and 1. So like for a irrational value, it will be 0, then it will be 1, then it will be 0, it will be 1. Okay, so the value will keep jumping between 0 and 1, and it's never going to settle at a single point, right? So we even cannot evaluate the limit. Okay, so even the limit doesn't exist in this case, right? So the function, so obviously we cannot satisfy this condition, so the function becomes discontinuous, which also implies that the function is not differentiable everywhere in R. So now we get the first property of this function, which is it is discontinuous everywhere in R, which also implies that the function is not differentiable anywhere in R. So we all know that differentiability the differentiability actually implies the continuity of a function, right? So if a function is differentiable anywhere in R, it implies that the function is continuous on that point or an interval, whatever. So now if we think contrapositively, then a function which is discontinuous somewhere in R, it will not be differentiable on that very point or interval, right? So now we actually get the second property, which is so now we got the second property of this function, which says that it is not differentiable anywhere in R, right? So these are the two most important properties of this function. So as we have talked about the properties of this function, so now we're going to talk about the applications of these functions, basically how we can use this function, right? So first we have taken a function, but the value of the function is x for rationals and 0 for irrationals. So let me draw the graph of this function. This is our 0, right? So we have x for rationals, so it will look like this, right? And 0 for irrationals. So now if we look closely at 0, here, so we can see that for 0 fx becomes 0. For f0 the value of this is 0, as 0 is a rational number, so it will becomes x and it is 0, right? And like if we consider this, like these two as lines, so we can say that these two lines from here, if we take this line, it is actually going towards 0. If we consider this line, it is also actually going towards 0, right? And if we took this as a line, so it is also like we can say coming towards 0, and from here we can also say that this part is also coming towards 0. So in short we can say that the function is settling at a point which is 0, right? So now here we can see that the function is actually settling somewhere, right? So which is 0 here. So now the function becomes continuous for the first time at 0 and only at 0, right? So the function becomes continuous only at 0. This is a very like important example of a function which is continuous at a single point, and in this case the point is 0, right? So as we have seen an example of a function which is continuous at a single point, now is there any function which is continuous only at 2 points, right? So let us take a function fx, x square for rationals and 0 for irrationals, right? So now if we draw the graph of this function, so let's say this is our 4, no, it will be actually 4. So the graph will be x square, so it will be like this, okay? And for the rationals it will be like this, okay? So now we can see that these two curves are actually intersecting at 2 points, right? Which is this is -2 and this is 2, okay? Now in this case it is intersecting at 2 points, so the function will be continuous at -2 and 2, right? So the function will be continuous only at -2 and 2, okay? So now the idea behind this kind of examples is to think of an equation with required number of roots, okay? So what I have meant to say is okay, so let's take an example. We need to find a function which will be continuous at only 3 points, right? So we need to think of an equation with 3 roots. So let's say x minus 3, x minus 4 and x plus 5 equals 0. So this is an equation with 3 roots. Okay, so the first root will be 3, second one will be 4, and the third one will be -5, right? So now if we put y equals to this, okay, so it will be the functional value is y, means this for rationals and 0 for irrationals, right? So the points of continuity for this function will be y equals to 0. So y equals to 0, and it will be this equals to 0, which will give us 3 roots 3, 4 and 5. Okay, so this function will be continuous at these 3 points, and it will be only 3 points where the function will be continuous, right? So this is the basic idea behind this kind of examples. Okay, so this is a very commonly asked question in examinations, which is prove or disprove if mod of y is continuous, then f is also continuous, right? So we all know that if f is continuous, we can say that our mod of x is also continuous, right? But this condition, which is the converse of this theorem, this is not true actually. Okay, so we need to actually disprove this with an example, right? So we need to find an example where we can show that our mod of this function is actually continuous, but the function itself is discontinuous, right? Okay, so for this, let's take a function if, which is 1 for our rational numbers and -1 for our irrational numbers, right? We've taken a function if x, so we have taken a function which is for rational numbers it will be 1, and for irrationals the value will be -1, right? So now what will be the mod of this function? It will be 1, obviously, because mod of 1 is 1 and mod of -1 is also 1. Now, so this will be for all real numbers, right? So now, as this is a constant function, this is continuous, this function is continuous, okay? But this is actually and kind of same as our Dirichlet function. So this is, as we can see, that for rationals and irrationals, it, like, the value of this function are different, so it is discontinuous everywhere. We have our example where our mod of f is continuous, and fx, this is actually discontinuous, right? So we disproved this thing. So this is another question. If gx is continuous, then both fx and gx will be continuous, right? So if gx, this is the product of fx and gx. First of all, we know that if fx and gx, okay, fx and gx both are continuous, then from here we can write that f gx, which is the multiplication of fx and gx, is continuous, right? This is a theorem, but this is not an if and only if condition, right? So the converse is not true. So we need to prove this. We need to actually disprove this, right? So to disprove this, we need to actually find example which will contradict this. So now we need to find fx and gx. So now for this kind of question where this is the multiplication of fx and gx, we need to find such fx and gx whose product will be a constant function, right? So and a constant function is always continuous, so this will be continuous, right? So we're taking if as 0 for all x in R, right? And we're taking gx like this, so it is -1 for rational and 1 for irrational, right? So now we know that if we multiply fx with gx, the product will be 0, right, which will be a continuous function. But as I've told you that this is an example of like a Dirichlet function, so it will not be continuous. Now what we can say that if gx, what will be if gx? It will be 0, as anything multiplied with 0 is 0. Okay, so fx multiplied with gx will be 0, and this is a continuous function. Okay, so we get fx gx is continuous, but and all this is continuous, but this is not continuous, right? Gx is not continuous. So this condition doesn't hold, right? So this is another question. Prove or disprove if composition gx, I mean this is actually so this is actually f of gx, right? So if this is continuous, right, then both fx and gx will be continuous. Okay, so first of all we know this, if fx and gx both are continuous, then we can write that gx is continuous, right? But this is not an if and only if condition, so the inverse will not be true. Okay, so that's why this will not be true, so we actually need to disprove this, right? So now let's take our fx and gx. So now again we need to find such f and gx where our f of gx will give us a constant function, so it will always be continuous, right? So for this, first we're taking fx as 0 for all x belongs to R, right? And gx, let's take -1 for our rationals and 1 for our irrationals, right? So now what will be our fgx? What will be our fgx? So now anything goes into fx will give the output 0, right? So it doesn't matter what gx we take, it will, the fgx will always be 0. So this will be 0 for all x in R, right? So this is continuous, right? This is now continuous as it is a constant function, and this is also continuous, but this is not continuous, right? So now this condition is not holding, right? So we disprove this.